I learned a few days ago about this new theory that I believe will revolutionize the way we do architecture, or at least it can. It's called the residuality theory, and I believe this is the right way of doing software architecture. Welcome back to Think Design Work Smart. I'm Alex Bolboaca, and I'm coming at you from the Mozaic Works studios. And today I want to talk about this specific theory called residuality theory, a theory that's been created by Barry O'Reilly. Now, I know a Barry O'Reilly, which I've met, but this is not that one. He's not the one I know is a business consultant. This one is actually an architect. But they share the same name, which is kind of fun. So let me talk you through what residuality theory is and why this is so interesting. The way we usually think about architecture is that we need to build a system that is pretty much static. So we start from by extracting some requirements. We figure out the non-functional requirements, which are very important for architecture. We figure out the use cases, and then we start thinking about how to structure this and how to have a system in place that solves all these problems. And I encourage my students, when we do architecture courses, to consider evolutions in the non-functional requirements. So what happens if we need to scale? What happens if we need to do more security and so on? And there's always been an instinct of mine to think about all kind of different situations and to figure out how these would apply to architecture. And sometimes those would be very, very weird situations. And it turns out that my instinct, I believe, is correct, at least according to this theory. So let me explain why. The thing is, if you look at architecture only as a technical perspective, you just see it separate from the rest of the system. Whereas in reality, your architecture is part of a socio-technical system, is part of a complex system, is part of the business, of a market, of something that keeps evolving. One of the characteristics of complex systems is that they will keep moving. Things happen and they just keep on moving. And I like how Barry put it in his talk at NDC London, which was, if a complex system stops, then it's dead, and then you can map it. So that's pretty much it. So our challenge has always been to create something that stands the test of time. What happens most of the time is that you create this system. You don't have enough information, because you never do when you start an architecture. And you learn little by little that there are all kinds of forces that push on your system and that pull it apart. And that results in you having to struggle and kind of challenge the system and refactor it and add new things and rewrite certain parts and so on. And that's the life of software developers. And it applies to design, so the structure of code, how we structure into objects, how they talk to each other, into functions. But it also applies at the higher level structure of components, services that need to communicate to one another. So now here's the interesting part that Barry noticed, and that intuitively I'd known, and I've applied for a while also in experimental settings, but he managed to get this really as a round theory. And that is, you have these stressors that come from the outside world. So your architecture is not isolated from the outside world. On the contrary, it communicates, it lives there. This means that everything that changes in the complex system around your architecture will push onto your architecture. And now a reaction to this could be, let's make this smaller. So instead of a monolith, let's make microservices. And then we have more things that are isolated, more or less. And so if things change around our system, then the probability that more microservices need to change gets lower, which is different from a monolith where you basically need to change the whole thing, redeploy, and so on. And so this is one of the key criteria that we use for decomposing systems. The evolution. How is the system likely to evolve? But one thing that I've noticed that was very weird for many people is that nobody thinks about this. Or, okay, not nobody, but most developers don't think about the structure of the code, and most architects don't think about the structure of their components in this way. They don't think about, what if that happens? Let's try to structure this so it fixes that future potential problem. And on one hand, we know why, because when we tried to predict the future, things didn't go that well. And so we became reactive, which is basically what Agile is, in trying to continuously adapt and basically trying to make your architecture kind of fit the new needs that we didn't predict that came up, but because we keep the system simple enough, we can adapt it quickly. But really the best way to do this would be some kind of a middle ground. A middle ground where you can figure which are the most likely things that will happen to your system and how to structure your code to prepare for those things. Only it turns out that there's a better way even than that, because the problem with that is that you need to figure out the risks, right? Figure out what other things that could happen. And this is limited by your imagination. But what if you could get there in other ways? And this is where this theory comes in. And it's really, really smart. I love it. So there's this concept of criticality in complex systems, which I'm not going to explain in a lot of detail. His talk is much better at that. But basically, imagine that you have an architecture. And imagine that some things happen to it. Well, it could be a new feature that you didn't plan for and that completely changes your architecture. It could be a new technology coming in. It could be a new a wave of users accessing your system. It could be hackers trying to take it down, whatever. And then when you have those are called stressors in this context. You have all these kinds of stressors. And you modify your architecture to respond to those stressors. And normally what we would do is we would do this in a reactive way. So when that happens, we adapt to that thing. And then the architecture is now adapted to that particular type of stressor, but then we get another type of stressor, and so on. Well, it turns out that in certain conditions, or at least according to this theory of criticality and complex systems, you can have this kind of random walk where you figure out what is the what are some stressors that you can apply, adapt your architecture to that, apply other stressors, adapt your architecture, adapt other stressors, adapt your architecture, and eventually you end up in something called criticality. And criticality means that your system is adapted to stressors that you didn't take into account. And that's where your system survives. So that's very, very interesting. There's much more about that, but I won't go into details. Let's see, however, an example. And the example that he gives is a car charging system. And so let's assume a naive architecture. You have electric cars, they go to charging stations. You have a login using a key fob. So you use your car key as an authentication mechanism. If the user is registered, this authentication returns OK. This allows the user to start a charging session. So this is a naive architecture. It solves the functional problem. And yeah, it could be a first prototype very easily. But then the thing that you can do is to do the stressor analysis. And here's the fun part, and actually the really interesting part. If you do this analysis for a large enough number of stressors, eventually you end up with imagined stressors that just work. And he gives here a few examples. So let's say, what would be a stressor? What would be something that could go wrong in your system? Well, a failed login. Okay, so the key fob doesn't work. It's not read for one reason or another. So what could you do? Well, you could do a technical change, which is automatic license plate registration. So you introduce a system that reads the license plate, registers the user, allows the charge and the invoices later when the user registers, for example. All right. And then let's look at another one, which was queues. So it was one which I don't find, but basically it was customer abandons car in slot. What do you do if a customer registers, places the car in the parking lot, starts charging and leaves the car there? Well, what you could do is a business change, which is an invoice per minute. So the longer it stays, the longer they pay. And maybe for the first 25 minutes or so, which let's say it's a normal charge, this is free, but then you can start charging more and more. Like the next 20 minutes, it's 10 euros. The next 25 minutes is 20 euros and so on. All right. So this solves another type of stressor. But then you get to this number 14, which is, so apparently some people are sabotaging the charging places by parking trucks that block the charging place. But because you had, there was another thing which was here with customer abandons car in slot. What you also need is a second, you need some kind of, you need more charging stations. So you need some redundancy. So now when it comes to this thing, which you wouldn't predict in a risk management session, this stressor is actually already treated by the fail login, because you read the license plate of that truck, by the damage thing, because you have redundancy, so because those stations can be damaged, and by the abandonment invoicing. So now suddenly you have a system that responds to all these stressors, to a new stressor, because you treated other stressors. And this is apparently, according to the theory, a property of certain systems. So it's where you can end up with this criticality. This is where you go. And a nice thing about this is that you can go in all directions here. So it doesn't really matter where you go. But if you apply enough stressors, eventually you end up to the point where you go into criticality, because you see for every new stressor that it's already treated, or for most new stressors. And this is really interesting. And the way to do this, then, because what we have is actually a network of things, but the way we can do this is by having the components, having the possible stressors, and doing this incidence matrix, where for each component we write a 0 or 1 for each stressor. So it's a binary thing. Does this stressor apply or not? Does this would this stressor take down this component, let's say, or affect this component? And then you can do an analysis on different levels. On one level, if one component has a high score of stressors, then that means maybe you need to protect it better, or maybe you need to split it so that it's less reliant on those stressors, is less affected by those stressors. If you get multiple components that have the same stressor profile, then you know those components can be grouped, can be merged. It's not necessarily to do that, but you know you can, because they will preserve the same stress profile, which means it won't get worse, right? It will just stay the same. And if you get a high value for one stressor, you know that maybe you need to do something to reduce that value. So to treat your components in a way that those stressors are not affecting so many components. And this is basically the method. And honestly, this is genius. I mean, it's based on science, on complexity science, which is the actual science that we also use in order to organize teams in an agile manner and so on. Many people don't realize that, but behind the whole idea of organizing teams in a large system and organizing teams as a self-organized and cross-functional, there's complexity science. So we have this already. We know that this works. And now this is a way of doing architecture that would allow us to create architecture that is stable over time by doing the right analysis. And I believe that many good architects, and as Barry is saying, many good architects are actually doing this automatically without any knowledge sometimes of the science behind it. It's just empirical truth for them. But it does make a lot of sense because I've seen it work in practice. And think about it. Why do certain classes from your code need change, but why do certain classes from your code become stable and don't need to be changed at all for long periods of time? And my guess is the reason for that is that those classes have lower stressors, have adapted to the stressor in time. Another way of thinking about this is I like certain complex survival games, and one of them is Frostpunk. And in Frostpunk, it's basically about managing a society that's post-apocalyptic. It's everything is freezing, and you have all kind of social and economic factors that you need to take into account. And there are some scenarios, but there's also a gameplay, like an endless play type of thing, where every few days or a certain period of time you get a new event. And that event could be something like the land is frozen, so you cannot farm, or you get the iron you get is very brittle, so you need more in order to build stuff, and so on. So, and what it happens with these types of survival games is that you start to get an empirical understanding of exactly this incidence metrics. Like, what could happen in order for my society to fail and for my build to fail? In that case, you have a limited number of stressors, but I've always imagined what would be with other types of stressors. And honestly, you can see this in real life societies as well. We get all kinds of stressors, and the question is, how do societies change in that context? So this understanding applies on so many different levels, and it applies on so many different levels because all of those are actually complex systems. What we have with architecture is really something that we want to be an order system, so it has very clear rules, and it doesn't change that much, it's very stable. But because it lives inside a complex system, it is forced to change. And ignoring that just leads to pain and suffering and annoyance. Instead, I believe we need to embrace it and keep thinking, okay, which are the things that could happen to our code that would make us change it. But the nice thing about this is that this goes to the next level, which is we don't actually need to take probability into account. The thing here is never think about probability. You can take a random number of stressors. Well, actually, the number will vary, but you could take random types of stressors, including very weird ones like Godzilla attacks our system or whatever, aliens invade, there's a pandemic, and it doesn't really matter because you will know you reach criticality if you get to the point where the new stressors are solved by the state of the system that you obtain. And I think this is this is the way to do architecture in reality. I think that solves the problem, a lot of the problems that we have with software architecture. So, a very interesting topic. I think this makes a lot of sense. Barry also wrote a book which is available on Limpub. I will link it in the description below, and I will also link the video that I screenshotted from. So take a look at this. Let me know what you think. I'm really curious. Did you apply this? Are you familiar with complexity theory? Does this make sense? Is there anything else that we should take into account? Let us know in the comments. Thank you kindly for the view, and until next time, remember to think, design, and work smart. See you next Saturday.